Hi, I am Thomas, and together with Tobias, we are going to present you our paper, An Open Platform to Teach How the Internet Practically Works. So let's start with this question. How do we traditionally teach how the Internet works? Well, first we explain to our students the theory, then we ask them to solve some exercises, and finally sometimes they have the chance to play with some real devices. This is great, but we think it's not sufficient to really understand how the internet practically works. And why is that? Because in practice first, network operators they often meet to make peering agreements. In addition, there are thousands of ISCs and connectivity must be monitored network-wide. So there are a lot of tools that are used in practice such as this connectivity matrix to help network operators to do that. And finally, debugging can be very tricky. Sometimes we run a trace route and we don't understand what is going on. So we need to investigate, and this is clearly not something easy. So for that reason, we actually decided at ETH Zurich to use another approach to teach how the internet practically works. We let our students operate their own mini internet altogether like if they were the network operators. So this is the outline of this presentation. First, I will show you how the mini internet mimics the real one and is entirely virtual. Then I will show you how the mini internet turns students into network operators. And finally, I will show you that the mini internet actually provides students with tools to ease operations. So on the right here, you have the AS level topology that we used in our mini internet last year. There are 6 regions in orange, and in each region there are tier 1 ASCs. By the way, they are all connected in a full mesh fashion. They are transit ASCs and they are stub ASCs. The ASCs they are connected with customer provider links or via peer-to-peer links. And also there are some IXPs that also interconnect some ASCs together. Now in each of the AS, we have an internal topology, and we always build the internal topologies following the technology that are used in practice. This means that they are layer 2 switches, they are IP routers, and they are also hosts. So this is the internal topology that we used in every AS last year. But when we build internal topologies, we always try to build like realistic internal topologies such that the student they have to solve real problems. So first, what we do is we assign bandwidth to each link, high, medium, or low bandwidth. And also in the layer 2 network, what we do is we say there are 2 types of hosts, staff members or students, such that our students have to configure VLANs later. And finally, there are also some VPN servers that are connected to some of the layer 2 switches and that the student can use to connect their smartphone or their laptop directly into the mini internet. Now you may wonder how we can run such a mini internet. Well, actually what we do is we rely on virtualization. So each component, a router, a switch, or a host, actually runs in its own Docker container. So then what we do is we connect the different containers together using virtual links and following the topology, and this is how we built the mini internet. And because Docker containers are lightweight, then actually the mini internet I just showed you before can run in a single server. For the routers and the switches, we just use the state-of-the-art software suite, so OpenVSwitch for the switches and FR routing for the routers. Now I am going to show you how the mini internet turns students into network operators. So what we do first is we give one transit AS and one IP prefix to each group of students, and their goal is to enable internet-wide connectivity. So first, they have to enable internal connectivity using OSPF, and then they have to perform some traffic engineering. For instance, they have to configure a custom spanning tree in the layer 2 network, as well as some VLANs. And in the layer 3 network, they have to configure load balancing. After that, we organize a hackathon where all the students they gather into the same room to configure the BGP sessions. So for instance, during that time, the students they really realize that they have to collaborate all together to enable internet-wide connectivity. Besides enabling the BGP sessions, we also ask the student to implement more advanced routing policies. So for instance, they must make sure that the traffic follows the business agreements, so they have to configure local preferences and they have to configure the exportation rules as well. And also we can ask the student to implement more additional preferences, So for instance, one provider is preferred over another. So during the project, we always maintain a connectivity matrix. On the X and the Y axis, they are the different ASCs, and then each cell indicates whether the two corresponding ASCs they can reach each other. So first, the matrix is fully red, there is no connectivity, but this year we managed to reach 100% connectivity, which means that the matrix was fully green. We are very happy about that, and that actually shows that the project worked well this year at TH. So now actually Tobias is going to show you a little demo of how the mini internet actually works.
Thank you, Thomas. So let's have a quick look at what is possible with our mini internet. After following the given SSH instructions, the students land in a so-called proxy container from where they can connect to all their devices. With a simple go-to command, we can for example access a router called New York. We are directly inside the CLI and can start to configure it. Let's have a quick look at our BGP neighbors. All of that seems to work well. With exit, we are back in the proxy container and can for example replace router with host to go to a corresponding host instead. Hosts are often used for debugging, so let's perform a quick trace route towards the destination in AS16. If we have a quick look at the topology which is currently running in the mini internet, we realize that starting from AS6 we will quickly reach AS13, for which we have to use one of the IXPs. From there we go over a customer provider link to reach the destination AS16, where we perform some internal hops. We can also see that there seems to be some load balancing going on, as shown in line 4 of the traceroute output. All these things will be experienced by the students when working on the project. We often observe that they quickly realize that the mistake is not necessarily coming from their own AS, but rather from one of their neighbors. They will then contact them and for example tell them that one of their policies is violated with their current configurations.
Thank you, Tobias. And now I am going to show you that the mini internet actually provides students with tools to ease operations. So first, our students, they do not have any a priori knowledge and they have a limited time budget. So what we do is we assist them. First, we organize Q&A sessions every week where there are teaching assistants that are here to provide help. And also we use a dedicated Slack channel where students, they can ask questions at any time. So for example, if they don't understand a trace route, they can post it on the Slack channel and then we will help them. And generally, the students, they like this way of communicating very much. Monitoring and debugging a network is also tricky. So what we do is we provide monitoring and debugging tools. For instance, we have a looking glass, which means that the student, they can actually look at the routing table of every router in the mini internet. We also give the ability to the students to perform active measurements such as ping or trace routes. And finally, we have a DNS server, so the students, they can use domain names instead of IP addresses. Students also are not familiar with routers and switches CLIs, so what we do is we provide them a documentation that is tailored for the mini internet.
Perhaps you want to now run your own mini internet. It's actually quite simple. Go to our GitHub page and clone the code. Follow the documentations, which mainly allows you to install all the software components. Then try to define your own topologies. For that, we provide very simple configuration files, for example this internal links config file, which allows you to define which two routers are connected together and what their bandwidth and link delay is. Similarly, there is also a file for the external links between ASs, where you can also define things such as policies between the different ASs. If you don't want to do that, we also provide all the old topologies which we used in our previous iterations in the lecture. Then just run a single command, wait some time, and hopefully your mini internet is soon running. With that, we are at the end of our short presentation, and we are happy to answer any questions.
All right, so we've got a few questions actually that have been coming on the Slack channel. I'll read them to you. So the first question is, what minimum system requirements are required for running the GitHub code in terms of RAM, CPU, and some other things? We can't hear you. I cannot hear you.
So perhaps I can take over.
Thomas,
By
you're
default,
muted. You were muted, Thomas.
okay.
Yeah. Can you try again? Because we've lost
Yes,
everything.
can you hear me now? Okay.
Yeah.
But that, otherwise,
Can you point your sound to the maximum? I think it's the problem that you just too low in loudness. No, doesn't work. Or maybe just Tobias takes over.
Yeah, I mean, perhaps Thomas can test a bit.
Sorry, yeah.
So for the requirements, I think that depends quite a lot on how large topology is and how much traffic you send, obviously. But for example, for this large mini internet that we were showing in the slides, I think we had a big server with like 256 gigabyte of memory and 64 cores. But I would say we had around half of that used during the project, but smaller components can be used on like 8 gigabyte of memory and like 2 cores or something can be scaled quite easily.
All right, so second question is regarding the mini internet, can the hosts run different networking stacks?
Yes, so there, I mean, we have to say that we obviously are quite flexible because we have all these Docker components and containers, and you can replace different parts of the mini internet. I would say that like for like testing purposes or things, we mainly build the mini internet with a teaching goal in mind at the moment. So we might not guarantee that we have like no packet loss or that everything works like 100% as you expected from a real environment, because for the teaching purpose, as long as the basics work, I think it's already great. But indeed, in theory, it's possible to use another stack or another protocol and test it as well.
And the question was indeed about testing. I actually didn't read the whole one, but it was indeed about testing. The third question is, do you also teach students how the internet can break easily, either by simple attacks or a BGP misconfiguration? Or by
actually, indeed,
as usual?
So I think part of it comes directly from the students because they do a lot of misconfigurations during the project. And then with this matrix, for example, you easily see that an entire part of it gets read and students start to ask, oh, what is wrong? And then one group no longer advertises their own prefix and nobody can reach them. But this year, for example, we also actively started to hijack a part of each prefix in each group or in each AS, and the students had to realize that like some traffic is no longer reaching the correct destination, and they can start to debug or advertise a more precise prefix as countermeasure. Okay.
And last one, but then fast, because I need to introduce the next speaker. They would like, the person who's asking would like to know whether the topologies developed in the platform can be somehow connected to the real internet.
I think so. That's actually a goal from us to add in the future. We don't have the support there yet, but in theory, you just have to bridge like interfaces or add some forwarding rules, and you should be able to do that.
All right. Well, I want to thank you for your great work, and it's not just great work, it's also one of the heavier hitters, actually the heavier hitter paper over the last 2 CCR issues. So thank you for making CCR popular, thanks to your work.
Thank you.
Hello guys, thank you for the presentation. So we have both presenters, Thomas and Tobias here. So Thomas, do you want to have the second try?
Yes, can you hear me very well now?
Yes.
Great.
Okay, so yes, it's a morning session. The procedure for the questions and answers is to post it on the Slack, or if you prefer, on the Q&A, which is supposed to be the first option, but I think most of the people are using the Slack. So let me start the questioning and bring up some questions from before. So what can you use it for? I know CDNs were mentioned and other features. So what can you support, and maybe more importantly, what you cannot support using the mini internet?
So indeed, as we mentioned yesterday, we can support additional features in the mini internet. It actually depends on what the software that we use can support. For instance, we use FR routing for the routers, and FR routing actually can support plenty of different protocols, such as MPLS, for instance, segment routing if you want to do segment routing, RPKI if you want to do RPKI. So it's actually relatively easy to integrate all the different things since it's already integrated by default in FR routing. And the same thing goes for Open vSwitch for the switches, and as well for the hosts. So all of this can be integrated relatively easy. So we are working on that actually. We hope, for instance, to teach multicast in an advanced networking course. And the things that we cannot do typically are the things that are not integrating in those tools, and that's harder to integrate. Yes, but in general, we can really teach a lot of stuff there. I don't have an example of what we cannot do. Someone mentioned, for instance, the Wi-Fi simulation yesterday. We can, for instance, simulate delay, packet loss, this kind of thing, but it's still going to be virtual links and stuff like that. So that could be one answer here. Yeah.
Okay. So one concern about the internet, I know, the real internet, if there is such a thing as the real internet, is about scalability. Right. So how scalable is mini internet?
Yes. So we have configuration files, and you can define your own topology. And clearly, if you use a bigger topology, like a 60 ISS topology, the one we used last semester, then you need to have a relatively powerful server. So in our case, we use a server with 24 cores and I think around 200 gigabytes of memory. But this is because when you want to run such topology, there are actually hundreds of routers, hundreds of switches, hundreds of hosts that are running. So I think with one server now, you can probably go even a bit further than that. You can have maybe an 80 ASIS topology, something like that. But clearly, at some point, you will reach the limit, and you cannot have like an even larger topology. So one option here, and we are actually thinking about that, could be to have two different instances of the mini internet in two different servers and connect them together, such that in the end we can build even larger topologies. So we are working about that. But for our networking course, like having like 60 or 80 ASIs is already enough, clearly. So yes.
Okay, and also I recall that Lorraine yesterday mentioned it's possible to use it for research as well. So can you, of course, the biggest impact we all do is through education and through other people, but in reality, we spend most of the time doing our own research. So, so those who want to get excited about mini internet from the research perspective, what can you use it for?
Yeah, so yes, indeed, you could also use it for your research if you want. Although it has originally not have been designed for that, but it can actually help as well for that. So, for instance, if you want to, I don't know, test some BGP conversions issues or whatever you want regarding BGP conversions, you can have a small network, and then you run BGP, and then you see what's going on. If you want to, for instance, to check, I don't know, like security, if you can detect that the traffic goes where it shouldn't go, and you want to do it in a sort of large scale with 60 ASIS topology, for instance, and you want to see what is going on, you could do that as well. So yeah, that's just a couple of examples of what you can do, and I believe that you can do more if you want to. Clearly, it just depends on what you would like to do for your research. Again, just to mention that if you want to, if you're looking for some performances regarding, for instance, the traffic, if you want to have a very low delay, if you want to do this kind of thing, then it might not be the right tool, because you are simulating everything in a single server. So the delay, for instance, might not be the correct ones. But if you just want to try things like which path are used, or how does BGP converge, then it could be the right tool, actually.
Okay. Tobias, do you want to add anything from your side?
Yeah, I think Thomas said that very nicely, but perhaps one thing is to have also bigger picture of like policies or different BGP policies, and you want to see how that converges or how that distributes in the internet. And I think there are a lot of possibilities. And for these kind of things, you can also remove some of the overhead that we add for the teaching, like a layer 2 network that you might not care for, like BGP conversion or something. And then you can actually scale the, let's say, AS topology quite a bit bigger. And we have an AS running where we have, I think, 100, 200 ASs, but they are smaller each. But you can have more, let's say, hops or more BGP connections, and then can test this way.